webinar is sponsored by Marubeni's Citizen-Cincom. Thanks for joining us. Here we're going to learn about how Citizen proprietary control technology offers one-button functionality to help speed and simplify setups on CNC Swiss-type lathes with no MDI or jog wheel required. The control holds data for the part program currently running. That data is used by the running system to enable a complex multi-axis Swiss type to be both safe and user-friendly to set up. Examples of key information include bar stock size, rapid approach distance, spindle directions, and potential collision zones due to the tooling systems used. Our presenters today are Brian Such, president of Marubeni Citizen-Cincom, and James Sabatino, an experienced company sales and applications engineer. There will be a Q&A session after their presentation. It's easy to submit questions, and I encourage you to do so during the presentation. You can simply type your question into the question pane on your screen, and we'll do our best to get to all of them at the end. So at this point, I'll go ahead and turn it over to Brian and James.
Thank you, Derek. Good afternoon, everybody. So as we wanted to do some presentation, we elected to review the Citizen Control again. And then we thought it would be a good take to maybe get a little bit of the thought process and the comments from the old guy and maybe from today's younger generation. And so we have James joining us today for this presentation. And so let's get right to it. And basically, before we talk about our control, I thought it would be a good idea to let's review a little bit of the history. And if we go all the way back, and maybe good, maybe bad, but I can do that. I was here before 87. And today's competitors, today's other controls all use what you might call near that standard FANUC control. And we did also back in the time we had the normal controls, and basically you did everything with MDI, manual data input. And some of you, if we do some history, we used to have the 3T, the 6T, the 10T control. But what Citizen wanted to do back then, being very revolutionary in the thought process of the control, and we basically came together and said, if we had a plan to do something for the future, let's take all of what we know today and all the concepts that we build on and throw it away. Let's get a new sheet of paper and let's try to say, what could we do that would be different, that would be better? And so we created this Citizen Control. And the main factor is to try to help eliminate human error. And what they found when they did their testing is some more than 80% of all crashes is when man was not involved. So, when man was involved, I'm sorry. So when the machine's running, it doesn't usually have any problems, but we stop to change a tool, and then we got to start it again. We stop to the end of the night or whatever you're doing and start again. We simply are adding a bar and cutting it off. The things that we have to do and the functions we have to execute on the machine was the biggest problem thought of the time. So back in around 88, we actually started a concept called machining data, and we're going to get into that in detail. And on our old L16 Yasnak control. And that machine was very simple. That control was very simple. It really couldn't grow much. Then in the 90s, we started to use Mitsubishi controls. But as much as the hardware is Mitsubishi, it's actually derived as the Citizen Control. We started to totally take over all screens and all function of the control and make it Citizen. And on just about every machine after, we have some form of Citizen Control utilizing what we call machining data. And so this is a key development at the time and a key function of how our controls work today. And I'm going to switch it over and let James talk a little bit about our machining data.
Thanks, Brian. So you guys right now are looking at a screen, and this is from one of our newer 800 series Mitsubishi controls, and this is the machining data screen. And the big learning curve when you come to Citizen is that we're not programming our machines with G54, G55 traditional work coordinates. We're using machining data. So you'll also hear us refer to this as MC data too. So the big thing is the machine's smart. It's going to know things like what the bar stock diameter is, what you want for a rapid position from the tool relative to the stock, what's the overall length of your part, how far is it sticking out from the front spindle or the sub spindle, depending if it's a Swiss machine or mill turn, and that's the premise here. So, and in this screen right here, it's showing on one of our Swiss machines if you're using an extended nose sub spindle collet. So instead of having to be on a standard FANUC control where you have to go and do the math and kind of factor in where the part is sticking out from the sub and go and set a work coordinate and then change that if you were to change your work holding in the sub, all that lives in MC data and the machine always pulls from it. So you even get flexibility out of this because if you set up the machine one way with, say, a 3/8 extended nose collet on the sub and realize for clearance reasons you need to swap over to a 1/2 inch, or if you want to change the projection of your part, like you can see Brian pulled up here, you only have to go to one screen and alter one value, and then everything in your program is going to refresh live from there. So then this right here is an example from one of our Miano machines, which are fixed headstock mill turns, so a little different than a Swiss. And this right here is from one of the FANUC models, but they all operate pretty much the same in that you get a cutoff position, which is controlling stock from behind the part to the front face of the main spindle. You have your machining length, which should be your direct overall length of the part as shown on the part print. And then you get a chuck tube position showing how far the part's sticking out from the sub spindle. And then lastly, you're going to have a chuck to chuck distance, which is just a value from spindle cap to spindle cap. So what's really nice about that is that when you're setting up the machine, if you're worried about clearances to the main spindle, and when I was in applications, I use this function all the time, I want to prove out my tool pass. I don't want to prove out preventing a crash. So what I would do is I would always artificially bump up the cutoff position, which is the stock from the back of my part to the front of the main spindle. That way, when I'm watching my tool pass, I don't have to worry about how close they become to the spindle. So that way, at the very end, I can look at it and go, I can change that down by a 1/2 inch to shorten everything up. I go back to my MC data, I change that value, and I can continue machining again without having to readjust any tool offsets, work coordinates, or transfer code.
So as we reviewed here, this is the basic concepts of our machining data. And so this data is actually attached to the program. It's not separate. So when you upload and download your CNC program, this data is attached. So now that we know there's information describing the part, all about the part in the control, now Citizen added a new feature, a new screen, where you have a mode called edit, you have a mode called MDI. Now we have a mode called preparation. Now, we still have MDI, but we don't want to use it. So our whole control has the data registered. Every button, every programming command is automatically using this registered data. And so as some of those data said, position point, and as our presentation description called, we can press a button, one button that says, call up this tool and cycle start. And actually 3 axes can move. And actually, if other axes are in not safe locations, they'll move out of the way before this tool calls up. And it's all automatic. It's all built in. We're not moving in MDI. We say tool 1, position point. Then every machine, like some of our machines are 5 6 axis. We go up to 11 axis, but starting, like you can't just start a machine anywhere, right? So we have a feature called start position. And if we execute this feature, Actually, 6, 8, 9 axis will move where the machine needs to be to run this part as described by machining data, which is not home. Some axes are home, others are where they need to be for this part. Then we also have a function cutoff. As I said, Citizen said back in the 80s, somewhere around 80% of all crashes was when man was involved. And why is man involved? He's cutting off a bar. What happens with cutoff? You have to make sure the collet's closed. You have to turn on the spindle. It sounds silly, but I have to say, you have to turn on the spindle in the proper direction, okay? You have to feed the tool down the stock to a right position, but also at a proper feed rate. Now, when a person is typing in MDI, which most other controls are, you can do all this, but I call it a fat finger. I have big hands. When I hit a button, I can hit 2 buttons at the same time. I think there's a lot of you out there like this. Or some of us are dyslexic and we're putting out numbers backwards. So I'm going to type in 0.003. I might type in 0.300. And so a feed rate of 3,000ths to 300,000ths is a big difference. And so we take away all of the person pushing buttons and we push a button, cutoff. Now, in machining data is the tool for cutoff, the speed for cutoff, the feed for cutoff, and the position. And so the programmer still has total control because he's setting machining data, but the operator pushes one button, cutoff. The spindle turns on and it feeds off nicely to cut the part off properly. If we ever are getting the machine out of a bad situation, the air went off in the middle of cycle, some alarm that we don't know. We have return position, and this says go away. A lot of you would call it home. It's not always home, but if axes are in not good positions, it's actually, even though you're saying move this axis away, it might move 3 other axes away first in an order that's best and safe. Get the tools out in Z, get the other side out in X, then bring this one away. So it's simple as a button press return position. The machine's going to move slowly and safely to a safe, proper position. And the biggest part of all of this is it's all safe without you having to think about it. Now, even if you use our MDI incorporates a lot of this. So we might simply say T200. And because of MC data, I want to explain in detail, what happens. So when we call up a tool, I got to click once. Hopefully I don't slide. Okay. Machining data had this positioning point James had explained. But as we set tools, they don't always set perfectly even. You can see here we got one way up, one down. And so all of our competitors will bring this slide up to a home position. I'm going to throw a number out there, like 6 to 8 inches up, then come over and come down with the tool they want. Well, what Citizen does is we know where you want to go. We know where all these tools are. We'll actually go up just high enough to go to the next tool and come across. And so if I was calling 2 tools next to each other, it might not come up very high. But if I was calling this inner tool, it's going to come up, over, and down. It does it all by itself very safely. And if we go to a added of machining data along with preparation, now we have very powerful options we call modular tooling. This happens to be a very common machine to us, our L series. And look at all these optional tools we could put in. This is a potential operator's nightmare. There's tools everywhere. They're pointing in all different directions. And then today I'm going to use this one. Tomorrow I'm going to use this one. They're all totally different. Boy, that is a nightmare. Well, we tell the machine we have each specific and each and every tool. And with that, when we call up a tool, we again just say, if you can see this little T11, that's tool 1100. And here's a little, it's on right now, tool 2. If I was on tool 2 and said T1100, that's it, one line of code. This machine is going to automatically move smart up in the air over in between these two optional tools over and in position. And there's no machine anywhere out there that works like this. And we started this in 1988. This is where Citizen is from, and this is the concepts that we believe in.
Brian, can you go back to the last slide?
Sure. I say before I go further, I want to ask if you want to add anything, James.
Good timing. So on top of the machine knowing how to safely jump from tool to tool, the other benefit that our control brings with it is you can see there's all these different configurations of tool positions. So you might be thinking to yourself, yeah, that's a lot of tools you could put in the machine, but I see a lot of setup time to teach the machine where all these different tool positions are, cramming my hand with an indicator in the guide bushing to try and sweep all these different X and Y pockets of live tools and static tools to find my center positions. So if you have a background of a FANUC-controlled Swiss machine, for example, you probably have to either write down all the XY coordinates for different live tooling or refer to a book to input them. But what's nice about the Citizen control is that in your MC data page is where you specify where these holders are going in and what tool offsets on those holders that you're utilizing. And from there, the machine actually pulls in all the core XY data to get to the centerline position of each and every one of those tools. So from there, all you're really setting is a longitudinal length of how far is the tool sticking out from the face of that tool holder. So not only is our control smart in the sense it can navigate around tools to prevent a crash, but it's going to expedite your setup time because it's less time you have to go and indicate in tool positions.
And then to go one more step, your operator, some of our operators are not as advanced as others. So when we're using the standard machine with simpler tools, the operator sees 8 tools. When we add the tools to the optional MC data, all of a sudden the operator will see 9 tools, 10 tools, 11 tools. So he's not forced to see 17 tools when he's only using 3. And so it only gets more vision when it needs to. Our competitors might have 20 tools sitting there, but they're only using 6 at the time. So it's very intuitive for the young guy or the less experienced guy. So James, I'll let you continue on this one.
Yep. So I guess one more point to add to that is all the tooling we've been showing you so far refers to our Cincom Swiss machines. This is still an example from a Cincom. This is from our M532, which is a Swiss machine with a turret, like a mill turn style lathe. But you can see how visual the control is, and all this will apply to our Mitsubishi controlled Mianos as well. You get the same holder setting page, so you're actually teaching the machine where you have an X-axis live tool, a Z-axis live tool. If you have one of our quad turning blocks that could have 4 OD or 4 ID tools, you get a really nice visual picture like this that shows the tool, shows the part number of the tool, so you can hold it in your hand, make sure it matches the part number on the screen as what you're holding. And then on the top right, it even shows an R1, R0 right below Brian's cursor. So you then specify to the machine which of those tool positions you're using, and that's how it knows how to pull in that data.
Previously, this would be done with some of you old timers with G50 shifts. What this does is the data is set. There is no G50 shift. And again, all of this data inputs and outputs with the program. So for the next setup, it's all there. And so we need to move forward. We got a lot of data to cover. So next is when we have this function of MC data, we have preparation that helps us set up the machine. Now you might have a 6, 8, 10, 12 axis machine, and we make a program, but is that program proper? So here's just an added benefit, a feature of Cincom and our Citizen controls. It's on Miano also, I'm sorry, Citizen control. And we call this high-speed program check. we don't have to run the program for a minute or 2 minutes or 4 minutes and find a problem and then go in the middle of cycle, try to fix it. We actually can sample run the program. What you saw, nothing moved. The machine control just analyzed the data, went through it, looked for syntax checks, looked for over travels, looked for illegal codes, and it actually also gives us a proposed cycle time, maybe within 10%. But we get past this feature, and now we know our program is close, and we're going to move forward and continue running the program. Anything more to add here, James?
The only other thing I'd throw in, just to truly show it's simulating, if you play that video one more time, Brian, and if everyone looks up on the top left where it's showing the coordinates, as this program runs, you're actually going to see the coordinate data of the machine change. So it truly is pulling in every offset, simulating every cut. So it's more than just the syntax of running through looking at the code. It's digitally running the program without moving anything in the machine.
So other features of just user-friendly and nice things that you may, even if you have citizen control, you may take for granted. And if you don't, imagine if your control had this. So the first is very simple. Push a button, M and G codes are at your command list. And some of our codes have options. All of those options called arguments would be here. So search any code you want, and you can say, how do you use that again? Okay, good. I got an example. Now, here's a great one called CNC code syntax checking. I'm going to call it my own words, and I'm going to call it CNC spell checker. So if you look in the upper right over here, first of all, we typically do the programs not at the machine, but I'm at the machine, I'm making an edit, I'm not an expert, and I typed in the wrong M code. I'm typing in what I think I want to add, the wrong M code, or maybe I'm typing X 0.2, but I did my fat finger again, X 0.2. Well, 0.2 is not good, right? It would alarm. Well, what this is going to do, live, immediate, right now as I'm typing, it's going to call it red, and it's going to say, that is not allowed. I don't even have to run it in the checker. It's live checking my edits right now. It's telling me what I did wrong, maybe. Then from there, I fix it, and the red line goes away. So code syntax checking, it's just standard. It's a feature we do. Now, this is a huge one, alarm retention and save. So tell me you haven't had this. You're working with your guys, they're less experienced, they get an alarm. First thing they do is look around. Is anybody looking? I don't want anybody to see that I have an alarm. They hit reset, they cut it off, and then they go to address the problem. What do they have to? Okay, we got to run it again. We run it again. There's an alarm here. I don't know. So maybe they play with it for 10, 20 minutes, reset. They go get their supervisor. He's going to come over. Hey, what was your problem again? Well, I don't remember. So he has to run it again. Now, every time you run it, you might have to recut it off. It's in the middle of a process, right? Well, if you cut it off, if you didn't, wherever you were, if you go to our editor after that situation, this rightmost screen is showing, it'll pop up with all the system showing where it was and the alarm it had. So system 1 will be where it was running, system 2 will be where it was running, and it will highlight the alarm. I mean, it's such a simple thing we take for granted. That is huge to save time to get your process going from a situation happening on the floor. And so, James, I'll turn it over to you.
Perfect. So this is one of my favorite options on our controls, and this is the sync display. So a lot of people have experience with 2-channel control machines, which are more and more prevalent, but now the more sophisticated machines can be 3-path control. So on a 3-path control, things can get pretty crazy because you can have 3 tools in cut. If you're going back and forth between where you're machining, if you're in the Miyano platform, for example, on almost all of our Miyanos that are multi-turret, either turret can cut on either spindle. they're not exclusive to one spindle or the other. So you're going to have a lot of different weight codes or different G600 mode changes, which is our machining patterns. And all that can be a lot to wrap your head around. So we have a function called sync display. And on sync display, what it does is in the smaller picture on the top right, that's our program, 3-path program load in the control. You can't see the code, but you can get the gist that all the blocks are kind of stacked on top of each other. But when you turn on the sync display option down there, it creates artificial space in the program, and the control will actually highlight all the corresponding G600 codes, which is our MC data, and our weight codes across any paths they might be used. So this lets you actually read through the program and see what sequences are happening when within your part machining, instead of having to look at the code on the top right like a conventional 3-path machine and have to bounce back and forth, look for this weight code, look for this weight code, and see where all those line up. So sync display is just a really good option for reading through your program, seeing what happens when, or even if you're troubleshooting your code, trying to figure out what other things could be going on when that program is alarming out.
And maybe our higher level guys are a different view. You press process display here, and it just takes on all the X's and Z's. It shows the T's and the queuing statement. So you have many ways to help you quickly troubleshoot, look at your program.
Yep.
Another great one. Go ahead, James.
So this is a good one. More often, we're seeing our customers utilize the milling aspect of our mill turn machines or our Swiss machines. So if you have an irregular shaped part where you're not picking off round on round, you're going to have an EDM'd or an emergency collet in your sub spindle. It's going to have to be machined to the shape of your part. But then when it comes time for transfer, you have to go in and synchronize your C axes between spindle 1 and spindle 2. So obviously when the sub spindle comes over, it doesn't crush your part or crash your machine. So right on our control, we have a control guided, step-by-step propped in process for synchronizing your C1 and your C2 axes for an irregular shape at pickoff. So instead of like other machines having to find a FANUC parameter for a C home position and grid shift your sub spindle based on the degrees you calculate that the main and spindle are off by, it's as easy as just jogging the sub spindle up, following the steps shown on the machine, and essentially pressing cycle start, and this control will kind of take control here, and it'll clamp the spindle, the sub spindle on the main, it'll rotate, unclamp, clamp again, and it's finding that perfect C-axis position on the sub spindle. So it takes a really daunting task of setting up a complex part on a complex machine, and it simplifies it.
When you get confident like we are in the control, you'll have this odd shape, hex, rectangle, weird thing spinning at $4,000, and you can, at 200 inches a minute, feed the collet on and not be afraid and know it's there. And until you've done it, it's a great thing.
It is. And then to go along with that, other options that we have in our machine that I think are just nice from these really more catered to the setup guy or the operator. They don't have to be a programmer and knowing all the G&M codes for engaging a spindle brake, advancing the parts ejector forward or backward. We kind of have what we call a peripheral device or an auxiliary device screen on our control, where you can just press a button and turn on the spindle 1 brake, the spindle 2 brake, send the ejector forward if you need to grab it and change it from part to part. So that's anyone who's done a changeover on a machine knows that if you're trying to change out your collet, you have to unscrew the main spindle cap and you have to turn on the brake so it doesn't spin on you when you're loosening with your wrench. So instead of having to look at a book, memorize an M code, you can just go to one spot on the control, say, yep, I want to turn on spindle 1 brake so I can take this collet cap off. And it just really simplifies that process for someone who's new. Anything to add, Brian?
No, I think we're good. It's just, and also that fat fingers, the operator is doing an M code to whatever function he's doing to bring up the parts catcher, but he did the wrong code. And now he turns on the oil or does something. So he doesn't have to remember these M codes and use MDI and have the chance of making human error. He pushes the button that is parts catcher, or he pushes the button brake, and it's a touch screen, and it's just wonderful, user friendly.
Mm-hmm.
And so now we've talked about multiple concepts and multiple little tips and tricks. And now I want to get into the things that you don't do that the control does for you. So there's a lot in citizen control that is built in. And I'm going to put these all up on the screen and talk about. So first is called, internal moves overlapped, decodes and mode selections. I already explained that we said T1100 and it moved in 7 different locations to get a special tool in safely and properly. But if we look at a different aspect, when the machine's changing the way it's running, so sometimes we're working on the subspindle on the back and turning on the front, and there are 2 different zones of the machine. And now we're going to change, and we want to do turning and drilling simultaneously. We'll show you that a little bit later. But the machines actually can think, know where you are, and instead of a generic machine with generic code, an axis might move, you can see my arrow, it might want to wrap it back, stop, know it got there, wrap it down to the position of the next tool, know it got there, wrap it into a safe. Well, what the citizen control does automatically, we used to call shock absorber control. Now it's smooth control, but it's actually in the rapids going to start moving the next command before it's finished, and it's going to round the corners, if you will. And so this is really another deep term, if you know deep, it's called in position check, and we're constantly checking it. And basically, it's going to make a smoother transition, and it's faster. Now, inside of that T code, 7 axes can actually move as a drill is coming in, and the other axes are moving to clear. So we don't have to make the main gang X safe, Y safe, up out of the way. Second side, Z safe, X safe, Z in. It all happens simultaneously in a way that tools won't hit. And at any speed, fast, medium, slow, it's the exact same movement, faster and slower. So let's take another command. Most all machines out there, some are, I'm going to say, getting better. Some are catching up to us. We had this for over 15 years. We don't have to have a spindle running, do a stop command, wait for it to stop, do a C-axis homing command, wait for it to go home, then say C 45 degrees. We're actually going to have a spindle running, have no other commands, and say G0 C 45. And as the spindle's slowing down, it's going to stop at 45. So we call this direct spindle indexing. And this might save, I've tested it before, today I don't know, 0.5 to 0.3 seconds. But every time you stop the spindle to go to C-axis, you're saving 0.3 seconds. This is many seconds in your production. Now, one more. Most of us, we all do threading. Threading is just threading. I don't want to think about threading. I just want it to thread. But if you go to a lot of machines while you're threading, put your hand outside the machine, it's very aggressive. The covers are bouncing, the machine, you can feel, you want to call it vibration or jerking. What you can feel is axis change motion at a high rate. What Citizen's going to do is, if you were to look at a normal threading command, it might wrap it in, confirm I got there. Go under threading feed, confirm I got there. Wrap it out, confirm I got there, and wrap it back. And there's your threading cycle. Well, our machine is again going to do overlap, or if you want to call it shock absorber control. It's actually going to wrap it in, make sure I got there, do the feed proper. But when I wrap it out and wrap it back, I'm going to round the corner here. And I'm going to round the corner to come in. This is all air. So if I round these corners, I'm not going to hit anything. but it's smoother and it's actually faster. We might save 0.1 seconds per threading pass. How much time is that? In the lifetime of a machine or in the lifetime of a week of threading, it's a lot of cycle time. Put your hand out. I give you a challenge. Pick any of your machines anywhere, stick your hand on the machine when it's threading. If you ever get in front of a citizen, put your hand on the machine while it's threading. You're going to feel the difference. It's unbelievably noticeable. Anything to add here, James?
No, they're all good points. If anything, the point about the direct spindle indexing is something I have to reiterate with customers because it almost sounds too good to be true. Everyone has this idea, if anything, it's bad for the machine or they're hurting the machine, that they need to run the spindle, stop the spindle, and then go into C-axis mode. But so if anything, in my experience, that's just been one of those too good to be true type aspects of our machines.
Key, all saving cycle time.
Yep. So if the sync display options, my favorite control feature that we have, the on-machine program check that we're going to get into right now is probably my second favorite. And this is going to tie in, again, to safety of proving out a part. So you have two functions here. You can use the sync display to read through your program and high-speed check to make sure that everything's good. But then you get into the handle check. So now when you actually want to start cutting chips, all of this movement here is being controlled by the pulse generator on the control. So you can see right there in that little sub window, as the operator turns the handle in forward or even reverse, the machine is going to move forward and backward in the program. So another thing to note here is this is controlling all rapids and feeds. So if you prove out your entire program, like right there, it's rapiding from tool to tool. If you prove out your entire program with the handle check, you have absolute certainty that when you run it at 100% rapid, that nothing's going to crash. What's even more impressive about this, when you watch this function on our Miano machines, it'll actually control the indexing of the turret. So it's a servo controlled turret index, not hydraulic or anything like that. So as you run it through handle, you're slowly going to see that turret indexed as it would in the normal program. So this is just another function we have on our control that can take a really daunting program on a really daunting machine and break it down so that the operator can prove it out with peace of mind.
I want to add a little bit here, James, and I just want to make it very clear. We don't have a rapid override. We don't have a slower rapid. We have an entire machine process override with our feed command. So we don't slow down the rapid, we slow down everything. And so, as James said, at a slower rate or a faster rate of the feed rate, everything's affected, even M codes. So you can guarantee that if we were at 10% and drilling here and with exit to the tool and entrance to the tool at 100%, it would all be in the same position. Yep. Very, very important. And one more concept is, as we're in the middle of that editing, now we're past all the checks and we're past all the other things. And maybe we're too good and we're skipping steps and we didn't do the high-speed check. If we got an error in that mode, we can actually live edit the program, fix it, and move forward through the program, not having to stop, cut it off, and continue. So in on-machine program check, we can live edit CNC code also. And then one more comment. Back in 1989, with an E32, we had this function. This is Citizen. This is Citizen Control.
Yep. So we can glaze over this slide. This is more of a refresher as it gets into our next slide. We're going to talk about how our MC data can simplify cutoff transfer code. So just to jog your memory, the machine knows where the tip of the part is. It knows how far you want it sticking out of your sub-spindle. So that gets us into one of my favorite programming commands, which is G550 or G650, depending on the machine that you're on. So G550 is going to be your high-speed transfer. And here we are. This is a sample of some code that I wrote for another customer where you're going to see us using, where the arrows are, G650. So it's a 3-path control machine. So we're going to do our high-speed transfer. So instead of, again, a traditional FANUC-controlled machine, handle jogging the sub spindle forward, do an inch in front of the part, writing down a B-axis position for the sub, and then doing math of how far to feed on, then how far to pull forward on a bar pull, I can write everything to my MC data pound variables. So everything you write in the MC data screen is going to correspond to a pound variable. Might be in the pound 800s, might be in the pound 100,000s, depending on the vintage of the machine, but they all operate the same. So what's really nice about this cutoff transfer code that I'm showing here is when you write this once and prove it out once, if you're always bar pulling with your machine, not bar bumping, where you cut off and then use the bar feeder to advance the stock forward, you never have to touch this code again. And for a lot of programmers and a lot of operators, this saves a lot of peace of mind, because in my experience, one of the most daunting aspects of running a mill turn or a Swiss machine is when the two spindles come within inches of each other and a turret or a gang comes rapiding in to part off. So if you know you have a proven structure that never collides with itself, and all you have to do is update your MC data in a very visual friendly screen, then you can use this programming format right here, which is going to call in X rapid to pound 814 plus pound 815. That's bar stock diameter plus position data. Or if you're going to bar pull and you're going to move your Z-axis by pound 818 plus pound 882, that's overall length plus cutoff tool thickness. So all you ever have to do to update your cutoff transfer code is update your MC data that lives with the machine. So this really is a good option.
This is our standard MC data, but it is accessible to the programmer if you choose. And when we start to do that, we create a whole new power to the programmer and the customers to set up and run the way they feel best with their operators. And now a standard format can be made. It's just wonderful.
Yep. Brian, could you go back to the last slide real quick? So one thing I want to note too, what you're seeing here is a screenshot from our book. So when you command G550 without any other codes, all the movements you see there of the sub spindle coming forward, the turret returning to home position in X before coming to a cutoff position in Z, all of those movements happen with one code input of G550. So the other aspect of MC data is it reduces the amount of code in your program. So that reduces the amount of error points of edits, and it just makes it easier for the user to read. So that one line of code is going to have 3-4 different axis movements at once.
And it's safer.
Yep, exactly.
I'm going to go into the next one here, which is my favorite here. So this is a Miyano using Mitsubishi, a BNX. And now with our citizen control on this Miyano, I'm going to stop it here. So a reminder from the other screen, it knows how far the part's sticking out. It knows what the length of the cutoff is of the part. It knows how much is sticking out of the subspindle. Now, what you don't know, it knows what's the longest tool sticking out of the back of the turret. It knows what's the longest tool sticking out of the front of the turret. Now, to show you the power of our control on a not Swiss machine, on a fixed head, we call fixed head a Miyano, this machine, the world would always send an X-axis home some 12, 14 inches away to a safe position and index, and then come back into cut. Then go to a safe position, index, come back into cut. What we're going to do is we're just going to say one T call, T200, T300, and multiple moves are going to happen automatically. So this just said was turning, and it's going to call up a drill. What is it? 0800. Did you see the distances move? It carved out a safe window in between the longest tools and the longest part. And I'm going to let this cycle a little, but it automatically knows. Now, next it's going to go back to turning. Notice it did not go out in X. So the tool changes are about 1.1 seconds versus 3 seconds, 3.5 seconds. Ooh, we're going to run that again. And so James, I'm going to let you, as the younger generation, talk about this compared to a previous model of a different machine.
Yep. So this also was a learning curve for me when I came to MCC, as just a background of being a programmer, a setup guy at just a regular job shop. So I had a background of running FANUC-controlled mill-turn machines. So I was used to running a twin spindle twin turret, but I saw what a machine crash looked like, and I saw how much could go wrong. So I knew how important it always was to do a GO G28U0 to home the turret in X, and then G28W0 to home the turret in Z to a safe area to index the tool before I bring it back in. So when I started working at MCC as an applications engineer, and one of the first machines I'm put on is a BNE 51MSY twin spindle twin turret machine similar to this, and the apps engineer that was training me goes, "Watch this." That was a moment where my heart sank when I saw those tools rapid back and with minimal distance. I think the buffer is 5mm, 3mm, 5mm, but
correct.
It's a tight value. But knowing that as long as you touch off all your tools and you properly use MC data to tell the machine, yes, this turret holder's on position 1, this turret holder's on position 5, the machine knows how to safely navigate that. So it's an
there's a huge difference. 5mm to me is a mile, and I used to change these to 1mm.
Yep. So it's a good option that, especially in a high production job shop where they're doing hundreds of thousands of parts a year, having something that saves a couple seconds per turret index, that'll amount to thousands of parts over a year that have been saved just from faster tool indexing.
We're going to jump into a topic next of citizen control, the superimposition. And today, some other builders and control manufacturers have versions of this. But I want to say again, back in 1988, we had 3-axis superimposition, 3 tools cutting on our E32. And so this is an example of, as we're turning a Swiss machine and multi-axis are moving, we can have another axis lock into, and I mean lock into, with intents, another axis, but yet to the programmer, you pretend nothing's moving and I'm going to program this drill in. And in reality, in the system, it's doing all the work. And here we are peck drilling at a normal feed rate, at a normal drilling. And since we have this power, the reason why you might not do this feature sometime is the RPM I need for this drill is slower than I need for turning. Well, when we utilize a live tool, if it's a small diameter, we might spin it forward at a high speed to get more RPM. But if it's a big diameter, we might spin it in reverse to get the proper RPM for the drill, but still have good RPM for the turning. So we have a huge vision here of superimpose. We have a lot to show you, so let's go to the next. And so this is from one of our Miano machines, and I'll throw it over to James.
Yep. So this was actually code I wrote for another customer on just a demo part for them. This machine's a BNA 42DHY3. So it's in the lineup of our Miano line. This is a more entry-level Miano. So it's nice to know that you have superimposition both on the entry-level machines all the way up to the highest-end machines. But what this was showing is one turret here with a y-axis able to machine 2 totally different features on the main spindle and the sub spindle simultaneously. So you can see as it was facing down the front, it followed, and we'll see that one more time. As it's facing down the front of the bar stock, the tool on the right side, which is on the sub, is following along and already starting to face on the sub. And then everything rapids away while still turning to do OD turning on both spindles. So it's a good option that's available, again, on entry level all the way to the most complex. And then speaking of most complex here, this is on one of our Cincom N machines. So this is actually going to show you 3 tools in cut. So what we're doing is we're superimposing the lower turret here to be drilling on the front, drilling on the back, while using the gang on the front side to OD turn. So on a 3-path machine, we have 3 tools in cut here. And this technology also goes over on the Mianos with our 3-channel machines, but 2 turret machines, because of the same technology of having an X-axis on the subspindle, I can get 3 tools in cut on a 2-turret machine. So you almost start to get triple turret performance out of the footprint and price point of a 2-turret machine.
And I want to start to say and keep repeating that you need to experience the difference with Citizen controls. This specific is probably in the 90s, but we could do this function in 1988, and we only grew on it over all of these years.
Yep. So then this is an example here from one of my favorite machines. This is the B&E MYY platform. So again, 2-turret machine. We're OD turning on the left spindle, and we're ID drilling on the subspindle here. So 3 tools in cut on a 2-turret lathe. So it's an immense cycle time saving on any high volume part.
So I'm going to keep us going. There is the ability for everybody to ask questions if you wish, and our moderators are going to present those questions. I'm not saying I want any. We're going to continue, but I'm reminding you, if there are any questions, please ask them. And so this one's just a fun one. I want to review. We have such technology in Citizen Control. If you can see this, here we go. This is a live rigid tap. This is a moving Swiss machine. Think about it for a minute. This tap can't just go in there. It's got to go in at a pitch and a feed rate to the tap as this is spinning. I'm going to be cutting an OD thread with this rapiding around. The tap has to follow it, wrap it in, feed in, wrap it out. It has to change RPM. This is 2 G codes. This is Citizen Control. So we call this a spindle superimpose. Also, we call it differential speed tapping. So we're going from turning on this side, and we're going to switch over and start to actually thread while we're tapping.
And I think the big thing here that Brian hinted at is this truly is controlled by 2 different codes. So this looks like extremely daunting programming, but all you're doing is programming an OD turn in one channel and a live tool tapping cycle in another channel, and just 1 to 2 G600 codes line all that up.
So we are winding down. We have time. We're going to continue. So high speed, James.
Yep. So the other aspect of the Citizen Control is with our Citizen Cav bar loaders, we integrate all bar load functions right onto the control. I think a lot of people will have experience using a third-party bar feeder. It has its own HMI. You have to go and set end-of-bar values. You have to input your usable stock length and a bunch of different parameters from job to job. So not only are you setting up a Swiss machine or mill-turn machine, you're setting up a bar feeder as well. Well, with the Citizen Control, with the Citizen Cap bar feeder, all that integrates right into the NC of the CNC machine. So our cab bar loaders don't even have an HMI on them. Everything comes from the NC of the machine. So these are a couple screenshots showing where you can go and set the parameters for your bar feeder. And my favorite aspect about this is all this data with there's a checkbox on the bottom right called auto setting. Well, you don't have to go and set those values. All you do is set up your MC data, check that checkbox, and it's going to pull in all necessary data to calculate those values for you. So it can make setting up a bar feeder a much more streamlined process. Brian, would you like to cover LFV?
This is a newer, should be for the young guy. This is a newer feature. So
all right, I can go over it. So LFV, important to note here, as Citizen, we are the original creator of LFV. So that stands for low frequency vibration. Other vendors have started to call it their own thing, oscillated cutting, all different names. But back in, I believe, 2016 is when Citizen pioneered this technology.
Right
so
2014,
so even earlier. So what's unique about LFV, and nowadays we can do 4 axes at once on our machine, is we're creating a controlled oscillation, whether we are turning, facing, doing a taper or an OD arc, drilling, and even threading. So what we're doing is on a very calculated level, we are bringing the tool in and out of the cut to create an inherent air gap the next time the tool comes back around the bar stock it's going to then go and clip the high point. So if you graph it out, it's 2 sine waves that you can stack on top of each other. So you'll always have an air cut. But what's critical about this is because we're controlling it, we are leading in and leading out of the cut. So we're not sacrificing any tool life, or if we are, it's an extremely negligible amount. A lot of our competitors who do this can't do the controlled lead in, lead out. So you're constantly re-engaging your cutting tool into a square shoulder on the part, and that's just going to create notch wear in your cutting tool. So this right here is an example that shows without cutting with LFE on the left, cutting with LFE on the right. I think this material here is like 303 or 304 stainless, notoriously stringy material. So the benefit of LFE here is it really helps with your lights out manufacturing. A lot of shops are pushing for lights out manufacturing nowadays. And one of the biggest issues, if you're cutting stainless steels or titanium, you'll get chip wrap on your part. You can't cut off or pick off without marking your part, tools breaking. So adding LFE into your program is something that can really enhance your ability to run lights out.
So as we continue and the possibility of questions, I'm actually going to play a video. You can just watch it while we, if there's any questions. So give me a second here. And I think that you could enjoy. This is basically a summary of many of the things that we talked about today. And James, can you just confirm to me that you can see this video?
Yep, I see it loading right now.
Okay.
So in the background.
And so if there are any questions,
yeah. So thanks, guys. Certainly great programming, food for thought, especially for such complex machines. So yeah, let's go ahead and dive into the Q&A session here. Got a few that have come in, but if you still have questions, please chime in. First question, are the tool data values loaded with a G10 command?
Go ahead, James.
All right, that's a good question. The T data values, so they're asking, do you have to G10 in? Do you have to manually pull in the tool offset to the code? The answer to that is no. Just by having the T200 and then a T02 after, that's going to pull in all your T data values to your cutting tool. So you don't have to worry about memorizing G10 with L and P values to properly pull in an offset.
And if that was theorized as a different question, our MC data, it's not offsets and G10s. Our MC data is a part of the program that uploads and downloads. So all of the tooling data, including offset data, is attached. There's no G10s. So please continue.
Okay, so we have an LFV question here. My current machines have an LFV limit of 3 axes. Can I go to a 4th axis with an upgrade?
I'm going to give that one to you, Brian.
Okay, so we actually have just made LFV better. And then just since July, Citizen has added the capability of doing 4-axis LFE. And what it is if you have a machine that's in the field and it already has LFV, with a software upgrade and an option purchase, you can do 4-axis LFE. I don't have the price right now. It's a low value, total rough, less than $1,000, and a software upgrade, and you can have 4-axis LFE.
Nice. Another question here. How is setting up MC data faster than using typical G54 work coordinates?
It's a good question. It might not be faster in the pure sense of the time it takes to set up the data, but it's going to become extremely faster on any repeat jobs since the MC data lives with the program. So whether you're on a traditional non-Citizen fan and control machine, you're going to have to do some button presses and input numbers for a G54Z offset, for example. Whereas MC data, you're punching in a few more pieces of information, like what your projection is on the main and sub, for example. It might balance out in the sense that you then don't have to go and do a complex transfer code to recalculate those values. But the big thing here is it lives with the program. So you set it up once And you never really have to set it up again, because when you call up that program, it'll call up the MC data. So any repeat jobs is where you're really going to take advantage of time savings.
And I'm going to add to that. If I'm making a program, I'm setting all that up on my PC. And so when the program goes to the machine, all the data is there and done, and I'm going to start to set my tools and run it. Where if you do the normal, typical G54 data, you don't know those numbers. You're going to touch off and set those numbers in the control, and that takes time. So I'm going to say MC data is faster. Next question.
Next question here. I use rapid override to better control my first running of a new program. Can I still do that?
Yes, you can. It's just going to tie back into what we touched into earlier. We don't have two separate rapid override knobs. A lot of legacy FANUC users out there might be used to a feed override and a rapid override. We just have one knob that controls both of them. So you can absolutely control your rapids, but you're going to control your feed rates too. And at the end of the day, that's really better because it maintains the synchronization of where the machine would be. If you take a standard FANUC machine and prove it out with rapids at 10% and feed at 100% and think, great, I finished my program, it's safe. Well, when you go to run that program again at 100% rapid, 100% feed, things will be in different places and you open up the door for a crash.
That ours is simpler and it's actually easier than two knobs.
Yep. Good question.
Gotcha. Yeah. So I said we're at the top of the hour here. I have one more question, and it seems perfect to end this. Where do you see citizen control technology 10 years into the future?
That's a good one. That's a tough one because just think of how much has changed since we started this in the mid to late 80s, like Brian started. I don't even know if Brian could have predicted all the different features that came out now, but just given what I've seen in my 6 years with the company, how much more visual the machine has become, I would really see Japan adding more to the HMI to make it more visual, maybe some degree of backplotting to simulate toolpaths in a 3D sense. I see the visual, the operator side of it getting dramatically increased. What do you predict, Brian?
I think magically the world and the industry can think that take a blueprint, put it in the magical software, and magical, everything's perfect. Well, we have 13-axis machines, and we don't cut brass. We cut Pastaloy, Inconel, 316 stainless. So the process is just as or more important than the program. And Citizen's always looking at what can they do to help users. And I think at today's stage of the game is education of the young people to even be able to get to that level. So again, in 10 years, I think the education will all be there and we can keep advancing. But we need, in some cases, people to catch up. Now, if it was to do it automatic, I want that also. And I would hope in 10 years we get a lot closer to that.
Agreed.
That's a great way to end this webinar. Appreciate it, guys. Yeah. Thanks, Brian. Thanks, James.
While I have a minute, I'd like to say thank you, everybody, for attending. Please experience the difference with Citizen, experience the difference with MCC. James?
Yep, pretty much the same. Thank you, everyone, for taking time out of your day today and coming to learn more about what we have to offer.
Awesome. Yeah. So on behalf of Production Machining and MCC, thank you all for joining us and enjoy the rest of your day.